Maybe we can start. Thanks for coming. Today we are very happy to have actually brought this week Boris Hanin from Princeton. A very short introduction. I mean, he's going to give a course, as you know, on mathematics behind networks. He studied his undergraduate studies were in Stanford. Then he did his PhD in Northwestern under the supervision of Steve Zeldich, working mainly on random waves. Then he spent a period as a postdoc at MIT, then at Texas A&M, a short period also at Facebook and Google Research, and now in Princeton. So he's been actually the best universities in the world until he came here to Vergara, which of course is and actually. Okay.
Scusate, ma da casa non si sente nulla?
Ora sentite?
Sì, adesso sì, grazie.
Okay, amazing. So like I was saying, I feel like the union of people's interests here is probably like everything you can imagine, and the intersection of people's backgrounds is the empty set. Okay, so that's like a very difficult challenge to attack. But thankfully, I was given 3 lectures, so we'll see how we can do. My plan in the first lecture is basically to give like a very non-technical, at least as far as I'm capable, non-technical introduction to what neural networks are. I don't want to assume that people already know and are experts. So I especially in this lecture, really in all of them. So stop me and ask questions. You know, I don't have a place I have to get to. I can skip certain things, or I can go faster or slower. So just let me know. And then the lecture 2 and lecture 3 will be slightly more mathematical, some basic theorems about neural networks, how people are thinking about them, and so on. But really today the goal is to first introduce what a neural network is, tell you how they're used, and then tell you what are kind of the big questions, at least some selection of big questions. Okay, so here I go. Let me start with the definition. Okay, so at a high level, a neural network is just some high-dimensional family of functions that's parameterized in a particular way. Okay, and to tell you the kinds of families of functions the neural networks are, I have to specify some parameters. So I'm going to define for you the simplest kind of neural networks. So they're called fully connected. So fully connected, sometimes called feed-forward neural network. Neural network, okay, so is any function of the following form. Okay, so here I go. So it's a function that takes in inputs x, and my notation is that the input dimension is going to be denoted by n sub 0. Okay, I hope people can read that from back there. Tell me if you can't. And the neural network is going to just compose a bunch of simple operations. So the first thing you do is you take your n0 dimensional vector and you apply an affine transformation to it. And you make a vector that I'll call z1 of x, which is just a matrix multiplied by x plus a offset vector b. Okay, and this thing lives in Rn1. Okay, so you apply an affine transformation. That's the first step. And then what we're going to do is we're going to apply a nonlinear function to each component of this vector, and then we're going to repeat the procedure. Okay, so what do you do? Now you form Z2 of x. Looks like this. You just treat Z1 of x essentially as the input to this layer, as it's called, of the neural network. So you take sigma of Z1 of x. Then you apply a matrix W2, add a vector V2, and now all of a sudden, because there's some justice in the notation, you end up in Rn2. Okay, I chose the notation for a reason. And you repeat this procedure some number of times, in particular capital L times. Then the output of the network is going to be C capital L plus 1 of x as the result. And of course, it's equal to W L plus 1 applied to sigma C capital L of x. It's B L plus 1 in R and L plus 1. Okay, so this is some way of producing a map from Rn0 to Rnl plus 1. And that for me is what a fully connected feed-forward network is. So let me circle some key things and tell you what they're called and why I give these notations. Okay, so maybe I'll do it this way. So these n's, these numbers here. So these are called the widths of the layers. So this is the width, for example, of the first layer. This is the width, second layer, and so on. Okay, very good. So these numbers are something you have to give me. It's part of the data of specifying a neural network. Okay, I give you a sequence of dimensions. You start with the first dimension, you end in the last dimension, and you do it by some intermediate representations in these other dimensions. Okay, so when I write this, maybe I should use a different color because I have a lot of nice colors. Excellent. Okay, so sigma here, this thing. So sigma is a fixed function from R to R, called the nonlinearity, or sometimes the activation function. And by the standard abusive notation, when I apply sigma to a vector, it just means apply it to each component separately. Okay, so the last thing I have to tell you is that capital L is called the depth of the network. This is the number of times you apply sigma. So when n equals 1, you apply sigma, and then when n equals 2, you apply sigma, and then when n equals L, you apply sigma. It's the depth of the network. So when people say deep learning, they just mean that L is big, like bigger than 1. Okay, so whatever I've done, I've specified for you a family of functions that goes from Rn0 to Rn1, and I haven't completely lied to you. This is a parameterized family of functions. Okay, it's parameterized by the values of the affine transformations themselves. So the entries of the W matrices are called weights, and the components of these vectors B are called biases for various historical reasons. Okay, by varying the W's and B's, you get different functions from Rn0 to Rnl plus 1. Okay, so that's the end of my definition. So let me just stop for a second, because if this isn't clear, nothing is going to be clear, and it's a total disaster. That's why I'm trying to kind of go slowly. Please stop. This, oh my God. This is okay? Yes? Must be a question. I feel it in my bones. Okay, I know what the question is, but yes, please.
Let's work upon it. Is that important? The sigma function, the activation function are all the same.
Okay, excellent. So it's funny. There's like an ergodic theorem at play. Every time I give a talk about neural networks, that's the first question that gets asked.
Okay,
so that's why I knew there was a question. So the short answer is, in practice, we almost always use the same sigma everywhere, but it's not clear that that's the best thing to do. But it seems to work, and so you don't know. But certainly you could put different sigmas, and it's a perfectly well-defined object. That's right. I don't actually have a second question. Okay, so here's my plan. I basically want to give 2 examples of functions computed by neural networks. Again, if you've never seen it, it's like a rather abstract definition. And then little by little, after we hopefully get a bit more comfortable with this, I want to tell you how neural networks are used in practice. It seems a little hard to believe that some insane object like this could be used to make a self-driving car. Okay, but like, I'll explain a little bit of that. So here's example 1. So let's consider sigma, our nonlinearity, to be what's called the ReLU. This stands for rectified linear unit, okay, a name only an engineer can love, I have to admit. Okay, regardless, this function is very simple. It's just the maximum of 0 and t. Okay, so in other words, your a ReLU network is just a network when sigma equals ReLU. Is very simple. Every time it sees a vector, if the component is positive, it keeps it. If it's negative, it zeroes it out. That's the nonlinear action that you get. Okay, so and then let me show you a way to draw a particular, like people draw neural networks not just in this way, but let me draw it like this. I'll explain the notation as I go, I hope. Okay, so I'm going to start with an input x. So this dot represents the fact that x is a one-dimensional number. So n0 equals 1. The input dimension is 1. And then I put a mental line here. Then I draw two dots. And this is going to be what happens in my first layer. So I'm going to write it like this. I get the graph. Okay, I have my weight matrices are going to be 1, 1. And then each of these things computes a sigma. Okay, I'll explain. Maybe it's obvious. I don't know yet. Those are the biases. Those are the B's. So this is a map which takes x and it maps it to sigma of. So you take x times 1 plus 0. That's the first component. So 1, 1, x plus 0 minus a half. Okay, this is my first weight matrix. This is my first bias vector. So map from R into R2. So n1 equals 2. Again, each of these dots is meant to represent a single scalar. And then this is my second layer. In the output, I have a one-dimensional object. So n2 equals 1. And my weights are 2, -4. My bias here is 0. Okay, and for fun, I'm going to put a sigma on the end because I can. Okay, so what do I compute? Finally, I compute. So this vector here is sigma of x, sigma of x minus a half. Remember, sigma acts on each component separately. And I just take the dot product of this vector with the vector 2, -4. So I get, and I apply sigma. So I get sigma of 2 sigma of x minus 4 sigma of x minus a half. Okay, so you'll often see neural networks drawn this way. So I wanted to at least indicate that you can represent matrix multiplication, something that a lot of us have seen before, in terms of a kind of graphical representation. Okay, that's all it is. This is sometimes called the computational graph of the neural network. Okay, is it clear the function I'm trying to explain? So this has, okay, n0 equals n2 equals 1, n1 equals 2. Those are the hidden layer widths that I have, input and output dimension. Okay, so now the question is, what kind of function is this? And indeed, that's going to be one of the themes that's going to pervade the lectures I hope to give. You know, even if I told you exactly what W's and B's you have at every layer, it's not completely obvious, at least not to me, what kind of function do you get? How do you describe it to a human? Okay, so humans don't think in terms of computational graphs. That's what computers use. Humans think in terms of actual graphs. Okay, at least the humans that I know. Okay, so this is a function from R to R. So here's R. So let's try to graph it. And maybe you can tell me, okay, this will be audience participation. So I claim there's going to be some interesting numbers, but let's see what happens. So let's suppose that the input x is less than 0. Okay, so maybe someone can tell me, what does this neuron compute? What's sigma of x? I want someone to say the words. 0. Okay, very good, right? X is negative. What's sigma of x minus a half? Still 0. Okay, come on. I know you can do it. Right, so point is when x is less than 0, you get the constant function 0. Okay, so now what happens? Well, okay, there's going to be an interesting input, which is x equals a half. So when x is between 0 and a half, what happens is this neuron turns on. Okay, I hope it's clear what I mean by that. It returns x, right? This sigma of x is just an x. But this sigma is still 0, because x is less than a half. So you just get sigma of 2x, but 2x is still positive. So you just get the function 2x. Good. So it goes up to the level 1. Next. Yeah, I'm sorry to do this so slowly, but I promise it's like a useful exercise, I think. It's also my favorite function computed by a neural network, so I can't help myself. Okay, so what happens when x is between a half and 1? So both of these sigmas are just the identity. And the total slope you get is +2 minus 4, so -2. So you get a function slope -2. And then past x equals 1, the final sigma turns off, and you just get 0. Okay, so this function has a name, comes up all the time in signal processing, whatever. It's called the hat function or the triangle function for essentially obvious reasons. Okay, so the point that I want to make, just to kind of build intuition, is the following. Okay, each time you have a neuron turn on and off, so for example, when this neuron turns on and off, it corresponds to a point where your function is nonlinear, it changes its slope. Okay, this neuron turns on and off, corresponds to this point, okay, or maybe this point. And when this neuron turns on and off, it corresponds to this point. Okay, so I'm just saying ReLU networks, at least if you have input and output dimension one, are easy to draw. They're just continuous piecewise linear functions. And generally, when neurons turn on and off, your slope changes. That's the kind of thing you're doing. So you can think of ReLU networks as a fancy way of learning piecewise linear functions. Okay, so I like this example because you can kind of get your. Okay, so let me stop again because I want to give a slightly more general example, but I feel like I should pause in case there are questions here. Is it clear? Am I just talking to myself? I need some kind of feedback.
It's very clear.
Very clear. So, clear as mud, as my teacher. Yeah.
First layer, when you write the description of the function,
Yes.
you did not write sigma in the first layer, on the first.
Yeah, and I didn't write it here either.
Yeah.
So that's an excellent observation. Typically, you do not apply sigma to the input itself. That's how you do it in practice. Now you could, nothing could stop you from applying sigma, but you generally don't. Now, I don't know what to say. That's just how it is. I got a real question. Okay, so very good. So this is one simple example of a function you can get, but this example contains more than you might think. So here's an exercise for those of you who are bored and already know everything. Okay, think about what happens when you compose this example with itself some number of times. You could, again, add the same neural network over and over and over and over and over, and you can get some sort of function. Okay, you're going to get something interesting. I won't tell you what it is because I want to do something. Okay, so very good. Very good. So little by little. Okay, so that's example one. Keep the definition up. So I want to do a slightly broader class of examples. This, of course, was just one particular function you can get. But it's, again, a class of functions all of us, I think, can get our minds around. And it goes like this. Okay, so again, I'm going to take sigma as value, but maybe I should say, for those that don't already know, in practice, this is the most popular nonlinearity people use. People use others, sometimes variations of this, sometimes rather different nonlinearities. But I'm focusing on this because it's popular and has some nice properties for writing it down. Okay, so here's going to be my example. This is going to be the example of all possible one-layer ReLU networks. Okay, so I'm going to take the input dimension to be 1. I'm going to take the output dimension to be 1, and I'm going to take my depth to be 1. Okay, so the picture for these networks, again, I find it helpful to write these pictures, is I have an input x, and there's just one dot because the input dimension is 1. And now I haven't told you what the hidden layer width is. Okay, so I have n1 neurons here, and I have output dimension 1. And each of these neurons has some weights associated. This is W11, this is W12, okay, down to W1 and 1. This is W21. Okay, you get the point. W2 and 1. Again, there are some biases and they all have signals. I'm not going to keep drawing it because it's a disaster. Okay, but the point is this. What's the form of the function that you get? So this node here computes in my notation. If you want, it's the first component of Z2 of X, and it has the following form. It has a bias. And then it takes the dot product of this vector in your hidden layer, okay, with the vector of weights that you have. So it's W2 sub j, these are scalars, sigma of W1 sub j x plus B1 sub j. Okay, that's the class of functions that you get. One hidden layer network. Sometimes people call these 2-layer networks, but I think it's more consistent to call it 1 layer. Okay, so let me ask you a question. So I'm going to write it as a lemma, which I will not really fully prove, but I'll say something about the proof. I'll leave it as a fun and short, I promise, exercise. So I claim it's pretty easy to describe what happens when you vary the B's and W's. Okay, so lemma's going to go like this. When W1j, W2j B1j and B2 sub 1 vary the space of functions you get, Z2, 1 of dot, I'll write it this way, gives all, okay, so I want you to fill in the blank. What kind of functions do you have? Okay, only answer if you've never seen the answer. It's not fun if you already know. Okay, like I'm just saying it's something relatively simple-minded. I take an x, I compute a linear function of x, affine function of x, and I apply max of 0 and t, and I add some things like this up. What kind of functions should I be getting? It's a function from R to R, so I can draw this again. Okay, so I get they go up and down, they're piecewise linear. That's true, continuous piecewise linear. Can you say anything else? How many pieces? Roughly. Okay, so right. So okay, very good. So it gives all continuous, I'll call it continuous piecewise linear. Okay, just allow me to make that abbreviation. Functions from R to R. So here's the precise statement. You can get every continuous piecewise linear function from R to R with n1 minus 1 breakpoints. So breakpoints are points where the derivative is discontinuous, where it changes its slope. Okay, and is contained in all continuous piecewise linear functions with n1 breakpoints. I'm being annoyingly precise, but I can't help myself because that's the way I am. Okay, so I'm saying you don't look too closely. Basically, you get all continuous piecewise linear functions that have n breakpoints. But okay, you have to be a little careful. Okay, so what's the proof? So here's my proof sketch. I'm going to put quotes around the proof. Who needs a real proof when you can have a fake proof? Right, so what's the point? So just think about this function computed by a single neuron. Right, so the function x maps to sigma of wx plus b, right, changes from 0 to wx plus b exactly at when the input goes through 0, right? At c is equal to minus b over w. Right, that's just the structure of a single ReLU neuron. So in other words, you just define the CJs to be minus B1J over W1J. So these are the points, like I'll order them for convenience, C1, C2, C3, and so on, where each neuron turns from on to off. Okay, and you get some function of the form like this. It has to be linear between them, but it's allowed to change its slopes. Okay, it does something like this. Okay, so you see right away that because each neuron can only turn on and off at one point, you can only get functions with n1 breakpoints. So that's clear. But you see, you get to control how the slope changes at each point. So because you get to control how the slope changes at each point, you get, it turns out, any function with n minus 1 breakpoints. It's like a little like stupid technicality. It's just at this breakpoint, you need to control this slope and this slope. So you lose 1 degree of freedom. So the point is that when people talk about using ReLU networks to learn or approximate some function, at least in this very simple case of depth 1 ReLU networks, all you're asking is find me a good piecewise linear continuous fit to my data. Something people have been doing forever. There's some particular way of doing it. Okay, so let me pause again. I won't give the rest of the proof unless people are desperate, but I doubt anyone's desperate to see this proof. Okay, there are more interesting proofs in life. And also that. Hopefully the building's not on fire. Okay, questions? Is this okay? Feel like there's a question somewhere. So I'm gonna slowly go to yours. Okay, so here's my plan. I'm gonna try to leave this definition up, okay, for a while. And what I want to do now is I basically want to tell you how in the world do you actually use a class of functions like this? to do anything in practice. And it's really the way these neural networks are used in practice that give rise to the mathematical questions that are of interest. And so I have to tell you something about it. Good. Also, I was told that people on Zoom can ask questions. So if you have questions, you should make yourself known. I don't know how, but I'm sure you can figure it out. Great. So let me talk about typical use of neural networks. Okay, like every person who does machine learning, everything I say is going to be a lie, but it's meant to be the truth. It's just that the lie isn't important. So what I mean is I'm going to simplify the steps of how people use neural networks, but I'm going to try to convey the essence. Okay, so step number one for using a neural network, typically neural networks are used for what's called supervised learning. Not that the name matters very much, is what I think of as data acquisition. Okay, this can be a very complicated step in practice, but since I'm a mathematician, I just call my function f. Okay, so what you do is you get a data set, I'll call it script D, of xi, yi pairs. Okay, I'm going to write I goes from 1 up to the number of data points. I hope people can see that. That's just pound of data. And the point is that yi, you think of as generated by a function f of xi, maybe plus noise. Maybe you get exact observations, maybe you get noisy observations. It depends on how ambitious you're feeling. Okay, and here's the key point. The function f is unknown. Okay, so how could you possibly get observations from an unknown function? Well, let me give you an example. So think like this. Imagine that x is like an image I take with my phone. Okay, I take a picture of the room. And f of x is 1 if there's a human in the image, and it's 0 otherwise. That's some kind of function that I could have. And now, for a human, we're very good at least approximately computing this function, right? Our brain is designed to recognize human faces. So if you give 1 million such x's, such images to people, they will pretty reliably tell you whether there's a human in the picture or not. So in this way, you can get samples from the function by asking someone to label it. But to a computer, an image is just a bunch of pixel values. And it's really unclear how to go from the pixel values to whether or not there's a human in the picture, right? Like, what do you do with the top left pixel? It's like, you take the cosine of it? I don't know. You got to do something. So that's what I mean. Like, your whole goal is to find an approximation to f, and we're going to search for approximations through families of functions roughly of this form. Okay, that's kind of the game we're playing. Okay, so step 2 is exactly what I said. You said, well, I have no idea what f is, but I'd like to approximate it. So I'm going to call this architecture selection. A statistician might call it model selection. So when people talk about the architecture of a neural network, what they generally talk about are things like the widths of the hidden layers. It's something you get to choose, and also the depth, and maybe also the nonlinearity, and other things I'm not telling you about. Okay, real neural networks can be much more complicated than this, although they all have this recursive structure essentially. Okay, so all this means for us is that you fix a depth, you fix some widths, and you fix a nonlinear function sigma. Okay, so since I'm not very good with formulas, I tend to draw everything. And I'll tell you how I think about this. And as you'll come to know if you actually listen to these lectures, I tend to think about things not very precisely. So for me, I think of this as a blob. Okay, so here it is. This is my blob. Okay, it's some kind of beached whale looking thing. Maybe it's got a nice hole in it as well. And what I mean is that each point in this blob, maybe this point up here, is some particular function you can get. So this is the function you get by some neural network of your fixed architecture. So again, the architecture fixes a finite dimensional space of functions. And I'm emphasizing that the space of functions is itself not linear. Learning with neural networks is not a linear method in general. Okay, so what I'm often going to write is I will put a theta here, what the machine learning people do. And the theta just means it recalls the fact that it has parameters. So the theta for me are all the w's and b's. Okay, by changing the w's and b's, I sweep out different parts of this space of function. And it's some kind of blob. Okay, and my hope this is the dream, is that somewhere over here, maybe there's a function that secretly does well at approximating f. Okay, so you can already tell, if you want connections to various areas of math, there are going to be a lot of questions in approximation theory. Okay, you give me a space of functions, it's a complicated space. How well can the space of functions approximate functions of a given regularity? Okay, that's like a classic question. Okay, fine. But we're not only interested in approximation theory, we actually want to learn this approximation. And the whole point is we don't know where it is. So what do? Okay, we give up. No, I'm kidding. We don't give up, right? We take a random guess and then we apply an iterative algorithm to improve our guess. Okay, so step 3 looks like this. You initialize. Yes. Maybe I'll call it initialization since I'm using that grammatical idiom. So initialization just means this. So it just means you choose your parameter vector theta. I'll call it theta at time 0, which again are just all the weights at time 0. We're about to do some dynamics. That's why there's time variable all of a sudden. You choose these things. Maybe I'll say randomly choose at random here. Okay, so all this means typically the distribution of each individual entry of the W and each individual entry of the B are very simple. So like they're just independent Gaussians, mean 0, and a variance that lightly depends on the architecture. Okay, so it's an easy thing to describe the distribution of your parameters at the beginning of optimization. But the distribution over functions you get is another matter, right? The map from parameters to functions is like very complicated. So the way I imagine it is you get some complicated distribution. Maybe that's like the density of the distribution. Okay, excuse my artistic ability, so to speak. But I mean that to be like the density function that you get on the space of functions themselves when you take a random theta. Okay, so what I'm saying is step 3 is you choose a starting point. This is like theta, this corresponds to theta of 0. Okay, now of course your starting point has nothing to do with approximating your unknown function because you haven't used the data yet. That'd be too much to hope for. So what do? Then you optimize. Okay, that's step 4. And at the end, I see optimization. So what's the goal of optimization? Well, the goal of optimization is to improve your choice of theta by asking that the function you get fits your data that you've observed better and better. Okay, so you improve theta of t by some variance of gradient descent. So GD stands for gradient descent. Okay, and maybe I write it this way. So gradient descent does this. It says theta at time t plus 1 is obtained from theta at time t by going in the direction of the negative gradient of some function that I'm about to specify for you. Okay, and this function is something you'd like to minimize. So L of theta is, for example, I'll put an EG here. People use all kinds of things in practice, but it may be the sum over your data points of the error you make on each data point. So you take the output of your neural network at xi and theta, you subtract what you're supposed to get, and you take the square. Okay, that's what you do, and you say, okay, by trying to do this optimization procedure, you're taking a small step in the negative direction of the gradient of L, so you try to make it locally smaller, and you hope that by driving L to be smaller and smaller, you fit the data you have better and better. Okay, that's the game you play. And so in other words, on the picture, what do? Well, you start over here, okay, and then you go off. And it's hard to know exactly what you do. Maybe you have a topologically interesting path, and you hope you end up in the place that you wanted to go. Okay, that's my cartoon. Okay, so you do this for some amount of time steps. Let's say t goes from 1 up to capital T. And then, okay, I can't help myself, so let me put a 5th step, which is in some sense not part of the optimization procedure, but you want to see if you did well. This is really the goal. Okay, so you measure, whether, I think that's how you spell whether, the function you learned, so z of x and theta at the final time of optimization is close to the y you're supposed to observe. Okay, so you draw a new data point and you ask whether or not, let's say with high probability, over a new draw of a data point x comma y, using, let's say, the same mechanism that you obtained data before, whether this is close with high probability. Okay, this is called generalization. When people talk about out of sample generalization or just generalization or whatever, like you don't care to memorize the answers on the data set you already have. You already know the answers there. You'd really like to make predictions on X's you've never seen, right? That's the kind of thing a self-driving car roughly would have to do. It drives around and takes some pictures of the world and all kinds of measurements. And then it says, okay, like, what do I see in here? Is there a human here? If so, where? Is there a car? You have to solve that sort of problem. I'm being very heuristic. Okay, so that's my typical use outline. So let me stop because I feel like there's kind of a lot to digest, especially if you've never thought about this. So I'm going to wait for some questions. Yeah.
What is the space, the so-called latent space?
I call it function space. That's typically what people refer to it as, but it's all kind of relative. Like the way I think about it is, for a computer, this is probably the best description of the function. Right? This is a simple recursive algorithm. Here's how you compute the output as a function of the input in some recursive call. But for a human, this is completely useless. So for a computer, I would say this is like the function space, so to speak. But for a human, when I write this, I mean something like, I think of the coordinates as being like the values at various points. That's something I can understand. Like on these images, you make such predictions. On these images, you make these other predictions. And between, when I start to talk like that, you and I can discuss it. So yeah, I don't know. I call it function space. I think that's what people. Other question? Yeah, please.
I'm just a curiosity, just some background. I'm an engineer, so I'm
Yeah.
funny.
Great.
I'm a computer engineer, so of course.
Okay.
So my case is I'm a reinforcement learning type of
Yes.
engineer. So sometimes what I care is that during the optimization process, I like not to get the right answer, but I like to get as fast as possible to a good answer.
Yes.
Which when I do reinforcement learning, I cannot say, I've seen colleagues say, I trained this network for 5 days, now it works.
Yes.
Because if I'm starting the car, I want to learn as fast as possible. So my picture, it doesn't say it is Mr. Smith, but it is a guy, or it is a human being, whatever. How fast I can learn matters more than I can do the right classification. And how this algorithm can be tuned to be as fast as possible, not to get to the right point, but to get as close to the right point as fast as possible. Is a way to do it, or is that relevant from a mathematical perspective? Because convergent speed in this complicated space looks very complicated to me, and sometimes the time to convergence is better than the quality of the final answer.
So remember how I said I was lying to you?
Okay.
Cool. No, but in all seriousness, I'm brushing a lot under the table, but your question is very reasonable. I've been necessarily imprecise. What do you mean by close enough? And so on. But surely one of the questions, in fact, I'll discuss, although mainly in the next 2 lectures, is there are practical questions. How do you actually initialize your parameters? What step sizes do you choose? You can make the step size eta depend on t. And indeed, what kind of optimization algorithm do you use? You always use a first order method. That's all you can really do in these systems. But there are many variants of such things. And proving theorems about rates of convergence for these various things is in fact quite interesting. So there are many like exciting mathematical questions which have a machine learning application. That's how I would put it. Yeah, so there's kind of almost a one-to-one dictionary, and I'll talk a bit about that. Right. Thanks. So there are comments or questions? Yeah, please.
It's not very clear to me what is the distribution of points of the block. How should I see it? The distribution with respect to the initial condition? Because you said that let's assume I start from Z over there, then there is that sort of green block.
Yeah, so I'm saying if you choose theta at random, that's just like choosing the W's and B's at random. So you get some probability distribution over the space of functions. And when you actually do optimization, what you do is you sample once from this probability distribution, and you use that as the initial condition to your iterative optimization algorithm. So that's precisely what I mean. This is supposed to be the density you get, and this is a sample from the density.
Okay.
That it's just the way I do it. Yeah, it doesn't not meant to be. Okay, should I attack? Okay, I'm already attacking. This is good. All right, so let me. I am going to do this. Let me I think we're pretty safe to believe this now. Keep the typical use up. So I want to now try to, as much as possible, to give a high-level overview of what are the questions that you should be thinking about if you're interested in doing theory of neural networks. I mean, I've roughly told you the procedure that people use, but the more you think about it, the more insane this procedure sounds. Okay, so let me start with that. So many of the questions are like, what in the world is happening? How can we make it better? And like, in what cases does it fail? How can you accelerate it? So on. So let me just start by something which I think is very useful in telling you about the magnitudes of the various numbers that are secretly floating around. Okay, so first of all, the input dimension, n0, right? This is like where the x's live. So think about an image. An image can easily have 1,000,000 pixels, right? That's not unreasonable for an image. And indeed, neural networks are often used in settings where the input dimension goes from 10 to the first, maybe even to 10 to the 7th. That's not an unreasonable range of estimates. So it's very high dimensional problems, first of all. High dimensional in the sense that each data point has a high dimensional input. Okay, so the hidden layer widths that you use, the actual dimensions of the representations, tend to be a little bit smaller than this. Maybe they're like 10 to the 1. Okay, I'll say to 10 to the 5 to be generous. Probably I should put 10 to the 4. I don't think anyone really uses it. Okay, so you take a pretty high dimensional input and you typically process it through hidden layers that are sometimes equally wide, sometimes a little less wide. Okay, but again, these are high dimensional objects. Okay, what about the depth of the neural network, the number of hidden layers that you have? So you should think of L as going from something like 10 to the 0 to 10 squared. Very deep neural networks have about 100 layers in them. Nobody uses deeper networks. It's very common to have like a 10, 15, 20 layer network. That's not an unreasonable estimate. Okay, so typically the width is significantly larger than the depth, and we'll see why that actually should be, okay, in the subsequent lectures. There's a principled reason, but this is what people do in practice. Okay, so the number of training data that you have is typically very large. So let's say 10 to the 4 or 10 to the 9. Okay, it's not unreasonable to have billions of training data points. At least in natural language processing problems, the training data sets are massive, potentially like hundreds of billions or like trillions of tokens. They're huge. Okay, so this is like, you have to actually compute, the loss and the gradient of the loss and everything on many, many data points. It's kind of a crazy computation to do. And then the number of parameters, in other words, the number of weights and biases in your network, is typically even larger. Let's say the smallest, like these days people will laugh at you if your neural network has less than 1,000,000 parameters. And if you're feeling really saucy, maybe you can go up to like trillions of parameters. Okay, so like we were just looking this up today with Domenico. Okay, so like the GPT-3 like model on which ChatGPT is based has like 175 billion parameters. Yeah, that's like a lot of parameters. So in other words, when I draw this like function L in this kind of simple-minded way, and I just say, okay, we're going to optimize data, you're roughly speaking doing optimization over like 100 billion dimensional space. That doesn't sound very reasonable. Okay, so the point of putting such big numbers on the board is, first of all, they're true. And second of all, it seems very hard. Like, what are the things we're normally taught in machine learning or, numerical linear algebra or numerical analysis or whatever, right? You're going to suffer from the curse of dimensionality. If you're trying to learn a function of 1,000,000 inputs, you're screwed, more or less. Optimization in like extremely high dimensions is always intractable. It can't be done unless it's linear, blah, 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 blah. But the point that I'm trying to make is that this is really more or less the recipe people use in practice. And it is, at least a priori, totally unclear why it works at all in this setting. Okay, so what I'm transitioning to is I want to state a number of kind of big questions that people are actively studying, but you can't appreciate them without seeing the kind of workings of what's happening. Okay, Okay, let me just pause for 1 second again. I'm about to make a transition. Yeah, please. Sorry.
You have more parameters than that.
Yes, almost always. And that's going to be a crucial thing. That is a huge, okay, that's an excellent observation. Typically, back in the day, they're rewriting all the statistics textbooks, I kid you not. They would say, if you have more parameters and data points, you're just going to overfit. You're going to learn a crazy fit to your data, and you're going to learn something which is garbage about making predictions. And that's not what happens with neural networks. That'll be big question number 2. Okay, so indeed, like I'm not kidding, it's very surprising to people who have thought about this for many years that this could possibly work, but it does. And so that's why it's exciting. There's new math. You know, there are new questions to be asked. Okay, I'm going to erase this. That's sad. No, I'm going to erase it. I told you I'm a liar. Okay, all right, big questions. What do people actually care about? Kind of, you know, empirical phenomena we would like to explain, / mathematical questions, which are like somewhat closer to doing theory. So okay, question number one, the way I think about it is the success, okay, not just me, everyone thinks about it this way, of non-convex optimization. So what do I mean by this somewhat grandiose kind of title? Well, I kind of mean literally what it says, right? So the observation is like this: the function L you're trying to optimize, which goes from a space whose dimension is the number of parameters. Okay, just let's say to the real numbers, it's almost always just the real value function, is very non-convex. I don't know what that means, but it's very non-convex. Right, so the reason is very simple. The output of your neural network is like an extremely complicated function of theta. And so, you know, each of these squares here is just an extremely complicated function of theta. It's neither concave nor convex. There's really no hope to classify it in those kind of traditional words. Okay, so it's extremely non-convex. Okay, but just a kind of local search. So i.e. gradient descent, right? Gradient descent is a local search. It just says wherever I am, let me look locally about what's the best thing to do and do that. So but local search almost always, not always, often finds a global minimum value. Okay, you expect a greedy local search to find a local minimum, for sure. That's what gradient methods are designed to do. So the kind of thing that at least I was taught back in the day is that you have a complicated function, like think of a spin glass or think of a random kind of function that is neither convex nor concave, its graph should look something like this. Okay, so here's L, and here's maybe the global minimum, here's theta star. And okay, it's a total disaster, right? If you start over here, for example, if this is theta of 0, maybe little by little, you'll go to this local minimum. This is, maybe I'll call it theta of infinity. That's where you'll converge. And so, you know, the typical story is that often in high dimensions, these complicated functions have an exponential number of local minima. And so why would a local search typically return a global minimum of the function? This is just like an empirical fact. Okay, so that's one of the big questions. And there's at least a partial resolution to this, which I'll present in the next lecture. Okay, but it's not obvious why this should work at all. Okay, so let me see if I wanted to, I wanted to give some intuition for them. I wanted to give like two kind of heuristics about why this might be possible at all. And then what I propose is we'll take a break for 5 minutes. Is that reasonable? Kind of. Okay, and then I'll come back with greater energy. Okay, but let me give you the two heuristics. Yeah, I encourage you to think about what could possibly be going on that this kind of like procedure actually works. A very interesting question. That's a lot of head scratching. Anyone have an idea? Who doesn't already know the answer? I'm a liar, but am I that much of a liar that it's secretly convex? No, I'm not that much of a liar. That would be too much even for me. Even for me. Okay, so I of course don't know your name, but the person who asked about the number of parameters question, that's kind of the key place to start. Okay, so I'm going to give you two intuitions. Okay, so intuition number one goes like this. Typically, neural networks, okay, I'm going to abbreviate them as NNs, okay, for obvious typographical reasons. are overparameterized. That's what it's called. Overparameterized. Oh my God, I don't think I can spell, but param. Okay. English isn't my first language. So they're overparameterized. So what does that mean? It just means precisely that the number of parameters you have, in other words, you can just think of this as the number of unknowns in your system of equations you're trying to solve, okay, is much bigger than the number of data points, i.e. the number of equations you're trying to solve, okay, which is itself potentially very large. Okay, so it's like the right analogy is you have an underdetermined system of linear equations. So from that point of view, you might say, but geez, that sounds great. There's a lot of ways to fit my data. Okay, maybe not so great if you're worried about overfitting. But from the point of view of optimization, I don't have this kind of like compact collection of local minima. They don't form these isolated points. They're like everywhere. Okay, that's kind of the picture you're supposed to have. And so what's the point? So intuition one is that therefore there exists infinitely many thetas that fit the data. Maybe I'll say that minimize. Minimize the loss value. Okay, so that's the first most kind of like down to earth intuition is that, yeah, you're optimizing over many variables, but that's actually good. In some sense, the more variables you have, the easier it should be to fit the data. That sounds good. Okay, very good. So let me get like slightly more precise about that. Okay, so moreover, let me just look at the form of the objective that I'm trying to optimize. Okay, so here we go. So in general, the thing I'm trying to compute is the gradient of the loss, right? And what do you expect from a local optimization? You don't expect it to give you a global minimum of L. You expect it to go to a stationary point, a point where the gradient of L vanishes. That's what gradient descent is going to do for you. Okay, so let's ask ourselves what structural form does this gradient have? Well, it's the sum on I goes from 1 up to the number of data points that you have of the gradient. Okay, I'll write it generically of whatever way you use to measure the difference between your current prediction on the ith data point and what you're supposed to get. Okay, so little l is like maybe the difference squared. That's the example that I wrote before. But if people use different things, my argument is not particularly specific to that. Okay, so what's the basic point? Okay, so let me ask you a very stupid question, just to make sure people are like, still there. So what is the dimension of this vector? Okay, maybe ask a student to answer. What's the dimension of the vector?
If you do probably tomorrow, you would have much less.
Well, that's okay, but there's only two parameters. There's number of parameters and there's number of data points, right? Yeah, number of parameters, right? So this is a number of parameters dimensional vector. That's what the gradient does for you. Now I only have number of data points of them. Okay, so very interesting. So what should you conclude? So if you're at a stationary point, okay, so I'm going to write an implication with some quotations because this is why it's an intuition and not a theorem. You should expect that these vectors are linearly independent, right? You have number of data points vectors in a much higher dimensional space, which is the number of parameters. So if the sum of them is 0, if they're linearly independent, what it means is that every single one of them is 0. Okay, so that's kind of amazing. So what this tells you, that there's no competition. There should be no competition generically between the data points. Usually what you're worried about is there's a trade-off. To fit one data point better, I have to fit some data point worse. And I'm telling you, that's not what you should expect in the overparameterized situation. Okay, so now, okay, let me do one more thing, I promise, and then we can take a break. Okay, we all know the chain rule. So let me apply the chain rule, right? This loss depends on theta only through the values of z. Let me write it this way. Let me write it as the gradient with respect to theta. So this is true for all I of zl plus 1 of xi of theta. Right? Just times the derivative of the loss, L prime. Okay, I won't specify where I evaluate it, but I just evaluated at these points. Okay, so now here's the point. I'm going to make the same point again, right? This is a matrix which is like very skinny and tall, right? This is a matrix that has dimension like, number of parameters by output dimension. Want to think of it that way? Okay, so just take the output dimension to be 1, just a scalar output. Easiest situation to think about. Okay, so this is just a single vector. And I'm telling you that this vector times the derivative of the loss. Sorry, maybe I should write this out more carefully. Okay, not so good at the chain rule, it turns out. So this is dl by dz. Okay, it's the derivative just in this variable, no longer in theta. At z comma y. It's not putting all the i's in there. So you don't expect this vector to actually ever be 0 for the exact same reasons as before. And so what you find is that at a stationary point, you expect the derivative of the loss with respect to z to be 0. But these individual losses, like this one, okay, they're complicated functions of theta, but they're very simple-minded functions of z. Typically, they're just convex, strictly convex functions of z. Okay, so in other words, finding a stationary point for the individual loss with respect to the output that you get is the same thing as minimizing. That's the point of convex analysis, or a point of convex analysis. Okay, so this implies, okay, quote unquote, that z of xi and theta equals yi for all I. Okay, that's my proof. That's like my intuition for what's going on. Okay, so is it kind of clear what I'm saying? This is very hand wavy, but it's just some kind of genericity. Like if you believe in algebra, geometric, things intersect in the right dimensions and vectors are random enough, you should basically believe that optimization is really easy. That's like what we'll prove. Okay, I'll indicate the proof in the next lecture, how it works for certain kinds of neural networks. But like making this precise in a more robust way than what we know how to do is like a big open problem. And it would be like a really nice way to resolve, in a sense, this question. So are there questions or comments about this? Kind of makes sense what I'm saying?
What's special about neural networks in this argument?
Nothing. That's why I like the argument. I don't think there's anything special about neural networks. I just think they're big and overparameterized and easy to optimize.
No. It's curiosity. I mean, this is a good argument because from an engineering point of view, it looks like we have a large neural network because it's cheap to implement them nowadays. So you are giving finally good mathematical argument why we should use very large neural networks rather than small.
Yeah, correct. I don't think it's specific again to neural networks, but I guess this argument for me says if the trouble you had before was doing optimization in high dimensions, you should take a model which is flexible and overparameterized. And then you should expect optimization to be easy. But when we come back after the break, so to speak, I'll point out that this has a downside. Optimization is too easy. Okay, but okay, we'll get to that.
Looks like overfitting is something should be something nasty. You have too many combinations that fit the data, which is the good one.
Precisely right. So okay, we'll get to that. I have a magic trick about that. Okay. So let's come back in 5 minutes. 3:07. Reasonable. I'll stay here to answer questions in case people have. Okay. So let me jump right back in. So the first thing I told you is that it's not obvious why optimization is successful. And then I told you it was obvious why optimization is successful. And I told you that I'm a liar. So there you go. So, but like I said, this brings like another sort of really deep and still very poorly understood thing. So I'll call it like this. I'll call it generalization with two things, with interpolation, in other words, exactly fitting the data. That's one thing, okay, and overparameterization. That's the other thing, parameterization. As a reminder, overparameterization means you add more parameters to data points. Interpolation for me means that you exactly drive the loss to a global minimum. That is, in fact, often what you do in practice. Okay, so here's the basic question. Here's how I'd formulate it. That's like kind of the moniker, everyone. Okay, so we already saw that when your network is overparameterized, you expect there to be an infinite number of ways to fit the data. So that's and the way I think of it this way, because I like to dramatize things. Okay, so among the C, think of it as a sea of global minima. Global minima of the loss. for some reason that we don't fully understand, gradient descent often finds some value theta, which minimizes the loss, but also such that z of x and theta generalizes. In other words, you not only fit the training data that you had, but you do well on data points you've never seen. Okay, that sounds great. That's like the dream. And that's why the actual people in industry use neural networks. They actually work. Okay, they're not only a mathematical construct. In fact, they are in some ways primarily an engineering construct these days. We don't understand why. Okay, so I want to actually unpack this in two different ways. And I want to say this. You know, when you're in the situation where you have an infinite number of minima for your loss out, in some sense, the most important thing after setting up the problem is to realize that the algorithm you use to do your optimization is what selects among the global minimum. Okay, so understanding how to make a map between the learning rules you use in practice and which kind of minimum you find for the loss is really the key to answering this question. Like most of the thetas you have are going to give terrible, terrible generalizations. They're going to be highly oscillatory functions that are totally garbage. But the thetas you tend to find are not like that. Okay, so I want to give you an intuition about why this is the case. And I'm going to give you an intuition in the only case where I can give a complete proof in like 2 lines. Okay, that's the only kind of intuitions I have ultimately. So you know, I started off by telling you that a neural network is a very complicated function of theta and so on. But now I'm going to do my favorite trick. I'm going to simplify. Okay, bait and switch is what we like to call it. That's what I call it at least. So let's consider the following situation. Let's just consider a linear model. Okay, so I'm going to have a loss that looks like this. I goes from 1 up to the number of data points. Now my model is very simple. It's just theta transpose xi minus yi on the squared. Okay, so this is my model z of x and theta. You just grab your input and you take a linear function of the input. Done. Okay, these are called linear models. Linear because they're linear in theta. Very nice. Okay, so what do we know? In this situation, so here, okay, I'm going to have the number of parameters. In other words, the dimension in which theta lives and the dimension in which x lives is much bigger than the number of data points. I'm going to give myself that. So I'm going to be overparameterized. And therefore, I'm trying to solve a system of linear equations, which is literally undetermined. Okay, so what's the picture? Picture is very simple. I just have to draw it. Okay, so here you are in R number of parameters, which is the dimension in which the x's live, right? And okay, what's the space of global minima? Okay, maybe just to make sure people are like alive in the afternoon, right? What's the space of global minima of this thing? I think it calls for another student to answer. How would you describe the space of global minima of squared loss over a linear? Okay, what's the value of the global minimum? 0, right? Like L can't be possibly less than 0. And when you're 0, it's just the space of theta so that their dot products with the given directions are what you want. Okay, this is just a hyperplane. Okay, so this is the space of minima. I'm going to call it I for the space of interpolance. The space of theta such that theta transpose xi is equal to yi for all of them. It's just an affine subspace. It's really easy for these linear models to describe. Okay, and as promised, there are infinitely many ways to fit the data because your problem's underdetermined. Okay, excellent. Very good. So, but now I'm not done. Okay, so the parameter space is naturally broken up into 2 important directions. And this is what we learn in linear algebra. So there's the direction which goes this way, and there's the set of directions which is parallel to the space of solutions. Right, so just a moment's thought tells you that these directions are just the span of the data inputs. X. Right, and these directions are the orthogonal complement to the span of the xi's. Right, these are the only directions in which you can actually change the loss. If you move theta in a direction that's orthogonal to all the xi's, you haven't changed the loss. So, you know, L only changes in those directions. And so you can only optimize going over here. Okay, very nice. So that's the basic thing. And now what's the point? The point that I was saying before is this is my sea of global minima, this yellow thing. And okay, there's one global minimum, which maybe looks appealing. So I'm going to write it in some way. And this is the minimum norm interval, theta min. It's the minimal L2 norm value of theta that fits your data. That's nice. But you can also, have arbitrarily large norm thetas and do crazy things. So now, but I told you that the most important thing for me is to understand what the algorithm does that actually does optimization for you. So let's work it out. It's not too bad. Okay, so here's the key observation. So let's compute the gradient with respect to theta of the loss L of theta. Okay, this is something all of us can do. If I can just find the loss, here it is. Okay, so obviously the gradient passes inside the sum. Okay, the 1/2 and the 2 cancel. It's almost as if I prepared the lectures ahead of time. Okay, and then you just have to take the gradient of this thing, right? So what do you get? You get the sum on I goes from 1 up to the number of data points. And what do you get? This thing is quadratic. The gradient with respect to theta only leaves the xi times the residual, theta transpose fi minus y. Okay, and what do we notice? Did I do all that pretty picture for nothing? Or am I trying to make a point? Sometimes it's hard to tell with me, to be fair. And get confused. But what do you notice about the structure of this gradient? Anyone notice anything interesting? It's right there, but it's hard to see, okay, as usual. What's its relationship to these two subspaces, the span of the xi's and the orthogonal complement? Please? So okay, I understand what you're saying. I'm looking for something like slightly different. Okay, okay, I will break the suspense. This just belongs to the span of the xi's. Right? The way you move your parameter vector is just a linear combination of the inputs themselves. That's all it is. So you see, it doesn't seem very complicated, but we just learned something semi-amazing. Okay, so semi-amazing, I'm going to switch to a different color. So what have we learned? If you start optimization here, this is theta of 0. Right? A priori, we have no idea which theta we got. But what we see is something very important, which is the gradient only moves you in the directions in which your loss has curvature. And so in other words, you only move in this direction. And eventually what you're going to get is theta of infinity is just that thing. So in other words, what you find is that theta at time infinity, the end of optimization, is nothing more than the orthogonal projection onto the space of interpolants of your starting point. Okay, so the way your optimization algorithm breaks the symmetry between these things is it says, well, I'm greedy and I compute the L2 based gradient. Okay, this gradient secretly chose an inner product to make its existence real. And it says, I'm going to find that minimum which is closest to me in the L2 sense, also known as the L2 projection. Okay, so what you learn that your optimization algorithm never unnecessarily moves you along the space of interpolants. You can never go this way. You never go off to infinity. Okay, so in particular, you get a beautiful theorem that I think is beautiful. If you just started at theta of 0 equals 0, if that's where you started your optimization, you're guaranteed to get the minimum norm interpolant. Okay, that's something called the representer theorem, equivalent proof of something in RKHS theory of the representer theorem. So it's really beautiful. It's like we didn't explicitly tell it that we don't want the L2 norm to grow, but secretly somewhere baked into our optimization algorithm was the fact that you decompose the original guess theta into its projection onto the space where you can't make progress and its projection onto the space where you can make progress. That's like the decomposition of theta of 0. And you can never change its projection onto the directions you can't see in the data. But this direction only can move in the space which intersects in a single point the space of interpolants, namely theta.
If you want to look for sparsity and forcing solution, why don't they start with the parameters equal to 0 rather than starting with a randomly say?
The short answer is theta of 0 equals 0 is not the exact right thing to do. So for these deep networks, it turns out to be a saddle. So indeed, as we're going to see, you actually take the thetas at the start of training to be small, but not 0. And like an intuition, that's why I wanted to keep this picture up, is by choosing a good initialization, in this case theta to be not too big, you're implicitly biasing the measure from which you sample your predictor at the start of training to be near simple functions. And then because your optimizer is greedy, it's going to kind of go as quickly as possible to the space of interpolants. It's not going to try to go out of its way to find a complicated. Now, okay, those are just words, but this is supposed to be the picture. For me, then. Other comments or questions?
Why theta mean performs better than other theta infinity with new data?
So the short answer is I didn't because it doesn't, but not always. So let me put it this way. Every theta on this space is the minimum norm interpolant for some L2 norm, depending on how you weight it. So I have to tell you something about the y's in order to tell you which theta is the best. But what I'm telling you instead is that the intuition is your algorithm doesn't unnecessarily increase the norm. That's like the intuition you get. Or more generally, it just doesn't force itself to find complicated functions unless it needs to fit your data. Roughly speaking, that's how I think. And there is a whole theory about why minimal norm is good and okay, but that's a classical statistical learning theory in RKHS space. I don't really want to get into it unless I have to. Questions? More questions or comments? So I want to say this was the intuition for what happens. Okay, sorry, I should say this is called implicit bias sometimes, or implicit regularization. Maybe I'll call it regularization. But there's a whole literature now on implicit regularization, and what that word means is that you didn't explicitly penalize the L2 norm anywhere in your objective function, right? That's what explicit regularization is, like L2 regularization. But your optimizer implicitly penalized the L2 norm in a sense. So okay. So
But what's done in practice, I guess, is some form of stochastic gradient for the organic.
that's right. In this case, it doesn't matter. Everything is so simple-minded. You can take full batch or anything. The point is, as long as your gradients can only be in the span of the xi's, there's only one, like your loss is strictly convex in those directions if you find it. But indeed, in practice, like, you know, there are variants of everything. It's unclear what they do, and sometimes they do very different things. Okay, so I told you why it's maybe possible to have generalization when you exactly fit the data. Or sorry, when you fit the data and you're overparameterized. But there's one more issue which is very important, okay, that I wanted to get into. So let me erase this. So this is the second kind of question inside of this big question. And it's again garnered a lot of interest in math and statistics and physics and machine learning, and all the fields that seem to care about it. So it goes like this. It's called benign overfitting. So let me see if I can do it. So here's the basic question. So recall that the way you generate the data, yi, is f of x, I plus noise. We typically assume that your measurements are slightly noisy. You don't exactly observe the truth, but you observe something like that. So the question is, why is it okay to fit the data exactly? Okay, that's what I mean by interpolation. And I'm really serious. People often will actually do this in practice. They will fit everything, the signal and the noise and whatever. And you're typically told that this is really bad. That's what I was always taught. But okay, the world is much more interesting and complicated. Okay, so let me sort of dramatize the situation. And I'll try to explain what we understand, and we understand even less in some sense about this, certainly about neural networks. Still, picture. Okay, so let's take a very, very simple situation. Okay, so I'm just going to try to learn a function with a one-dimensional input and a one-dimensional output. And maybe I have some training data points and they look like this, 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 I don't know. Okay, so, well, what can you do? So let's imagine trying to learn this by polynomials of degree 0. Okay, I'm sorry to tell you things you already know, but maybe you haven't seen this kind of picture. So I'm going to think of overparameterization as increasing the degree of the polynomial I'm trying to fit my data. I have more coefficients, therefore more parameters. Okay, so if I try to find the best constant fit, maybe this is the best constant fit that I find. Doesn't much matter. And it doesn't do so well, but it's not totally crazy. Okay, if I take the best linear fit, so maybe this is degree 0. Okay, maybe I do this. That looks good. That like degree 1. Well, it doesn't fit exactly. Okay, and now what do you know? So there's a unique degree 2 polynomial that fits these 3 data. Okay, very nice. Dry. That's degree 2. And now you start to get worried. Okay, now there's infinitely many degree 3 polynomials that go through this data. And the thing you're concerned about when you're overparameterized, if I can find a reasonable color, here we go, is you basically, with a high degree polynomial, will learn a fit that looks something like this. Okay, so this is degree 1,000. Okay, it doesn't actually look like it's degree 1,000, but it doesn't matter. You'll learn just something that passes through the data, but it's highly oscillatory. That's like the picture in every statistics text. Okay, so let's imagine that I told you that the data was actually generated by this linear function here. This is my true data generating process. And I just observed this linear function with norm. And so maybe degree 1 was a good thing to do. Okay, so now here's my challenge to you. Can you think of any functions that both fit the data and do well on data points I haven't seen? I'm saying that's what actually happens in practice. What kind of functions could they possibly be? Oh, very interesting. Maybe I draw them in red. But that's like the thing I'm trying to say. Like, we don't know how to prove this theorem exactly, but there are like attempts and simplifications or whatever. But there's a conjecture for what these functions basically look like, and you'll see that the conjecture has a lot of interesting implications. Anyone? What can the function look like? Yeah. Okay, fine. But what's the structure of the pieces? Like, how can it exactly fit these big deviations from the truth and still be close to the truth? Okay, so let me break the suspense. All right, so here's how you can do it. Well, you basically return the truth, and then very close to each of these data points, you have a little spike. That's an example of a function that fits the data and generally does very well away from the data. Okay, and basically the conjecture is that overparameterized models essentially do this. So how are you supposed to think about this? Okay, so the moral of the story, this is kind of like my moral. Okay, so this is a line of work that sometimes called benign overfitting. And so overfitting is the situation where you make these bad blue predictions, and benign overfitting is where you make maybe not the so bad red predictions. But the story of benign overfitting is that, okay, I lied to you, and this time I lied about something important. Okay, what do you like? In what sense is this a good fit? Okay, so the red line is a good fit in, for example, L2. Right, like for most inputs, it's pretty good. Okay, but okay, you have to pay a price. There's no free lunch, but it's very bad in L infinity. Right? You know it's bad because at the training data points, you make a terrible prediction. You're guaranteed that you shoot yourself in the foot. So the truth at the data point you observe is really far from what you actually observe. And you insist on finding a function that exactly fits your data. So you know that at your data, you're making a large L infinity error. No, the L2 error is small if the base of this thing times, the square of the height is not too big. So the philosophy of this line of work is that what happens is you use high frequency components of your model of your neural network, high frequency because they have to be highly localized like this to actually fit the data locally, and low frequency to actually fit the signal. And you do it at the same time, okay? Or you do it in one optimization procedure. Okay, so maybe I'll write that. Say low frequency fits the signal, high frequency nuance. And maybe if you don't care that much about the high frequency components of your prediction, you're fine. But there's a whole world of people who think about what are called adversarial examples. Okay, this is the phenomenon, which I won't talk about too much, but is really fascinating, honestly, that basically every neural network you've ever seen in your life can be fooled by small perturbations of the inputs. Okay, so like you have something which is 100% sure that it sees a stop sign. Okay, the neural network people actually use in self-driving cars. And then you put a tiny little post-it note on the stop sign, and it's 100% sure that it's a fire hydrant. Okay, that's not great. Not great at all. And so what I'm saying is, near interesting data points, like the training data points you have, small perturbations change the function a lot. Okay, and like at least this is kind of consistent with that story. So can you prove this? Can you make this better? Or what should you do? Okay, I don't know. You ask me.
So this depends on the loss function that you're choosing.
Correct. So you typically choose something that's like L2 or LP, let's say, whatever.
So if you train the neural network with two different loss functions, like L2 and L infinity, and then you take some mixture of the two, then you could avoid this sort of problem.
Well, training with L infinity is hard because it's not differentiable, but I take your point. You could train LP for P high enough. But okay, it's an interesting open question. We don't know what P to choose. We don't actually, like, this is just a picture. We don't know the width. Okay, but like that's a very interesting problem. Honestly, it's not an easy problem at all. People think about it and they failed pretty spectacularly. So, please.
Because this looks like what you would like to have in every type of program. You care to have small error on not observed data, and that you can accept that the high dimensionality fits the data you actually have. This looks like the fact you want to have even before starting to discuss.
So from that point of view, it's optimistic. That's right. This is the best you can hope to do if you insist on fitting the noise.
It looks like magic.
So indeed. But the way you should think about it is generally the low frequency parts of the prediction function are able to train faster. So what people see in practice is you first fit the signal, then you fit the noise. So you can even do somewhat better if you stop early. Okay, there's a whole world of people who do that.
This answers my previous question. We want to converge fast to something decent.
That's right. Indeed. Precisely. So, but I'm just saying this is the picture that people think, okay, we don't have exact proofs. Okay, questions or comments about this? I want to say a couple other things, but. Right. Okay, we're doing well. Right on. It's okay, right? So like, yeah, I don't know. I find these to be like fascinating questions. I haven't exactly made them into fully mathematical questions. That would just take more lecture time. But I hope to like at least convince you that there's like kind of profound phenomena, and all of these have really beautiful not analog, but like specific questions that are rather classical and mathematical. Things about Hilbert spaces and non-convex optimization and functional analysis. I don't know. I'll get more into the math in the next lectures, but I'm going to try to keep this high level for the rest still. Okay, so there's one more thing really that I'll say. The third kind of question. Okay, so this is what's called transfer learning. Sometimes it's called feature learning. And let me explain what this means, but you may have already seen these words, or maybe you're an expert and know what these words are. Okay, so here's another phenomenon. This is, in some sense, why people actually care about neural networks in a way. This is maybe the most important thing about neural networks these days in practice that they can do what I'm about to explain. And we're kind of hopelessly lost at the moment to explain how it happens and what you can say. Okay, so here's the question. Okay, so the output of a neural network looks like this. So I'm just reminding you, remember my notation was that at L hidden layers, okay, let's say at the ith component of the output, at input X to the network. So what did this look like this was just a linear function of the last time I applied my sigma. Right? It had the following form. I'm going to turn off the b's because they don't change it. So it's just a linear combination with some learned weights. These are the weights in the last layer that go into the I component of the output from the j component of the previous layer. And I have, I'll write it this way, phi j of x with some parameters theta, okay, where phi j of x, the parameters theta is nothing more than sigma of the j component of CL of x. You hear that statement? Right? The final output to the network is just a linear combination. Okay, I dropped the bias out in front of the thing you got from the final hidden layer after you applied your last sigma. Okay, so why do I want to say it this way? You see, if you didn't have a theta in this phi, and you just had a linear combination of a fixed set of basis functions, this is what people call linear models, right? They're linear in their parameters. The interchangeable parameters would be these W's. But the point is that you not only learn the coefficients in the linear combination, you also learn the basis functions themselves. Okay, so this is very important. So optimization, hey, whatever you do, gradient descent, Gaussian gradient descent with momentum, and blah, 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 blah. Okay, so optimization does this. It learns both the coefficients, okay, these WL plus 1 ij's, okay, and simultaneously learns the basis, phi j of x and theta. Okay. So often, at least in the machine learning world, the basis functions are called feature functions. They're like the kind of thing where you say, okay, if x is an image, I'm going to compute these interesting functions of the image, and then I'm going to use those features to make predictions. Okay, think of phi 1 as, is there a whisker in the image? Phi 2, is there a head in the image? I don't know, is there a wheel? Like interesting nonlinear functions that might be useful for my problem. And then I say, after I've learned an interesting basis in which to represent the image, maybe they're wavelets, that's like a more mathematical example, then I'm just going to learn linear combination of like the wavelets that you learn. Okay, but here something much more profound is happening in a sense. So maybe I'll put the theta back in here. You're simultaneously learning both the basis, i.e. the Hilbert space in which you're secretly working for your kernel method, and the coefficients in the linear model that you're going to learn, i.e. the linear combination of the basis that you're learning. Okay, so the basic question is like this. What properties of the training data of xi, yi, in other words, more precisely, if you think of the xi's as randomly sampled, and then the yi's as being like the observations of your unknown function. So what statistics of your data generating properties do we learn? Do we encode in this basis phi j? Okay, so one of the most successful ways people use neural networks these days, like if you do natural language processing, for example, they use what are called foundation models. You take one ginormous network, okay, with 1 trillion parameters in it, and you train it on a massive data set that you've somehow gotten by scraping the internet, all the possible sequences of tokens, okay, whatever. And then what you say is, you say, okay, amazing, by training on that data set, I'm gonna learn a good basis, phi j. And then what you do is you take your favorite problem you actually want to solve with the neural network, and you do transfer learning, okay, that's what the transfer means is. You basically just retrain, for example, the final layer weights here. You use this as a way of learning an interesting representation of your words or your characters or whatever you had, and you learn a new linear combination of this good basis. So this works extremely well in practice, and we don't understand why. There's not even actually a language precisely for talking about what bases are good and what bases are bad in a way that plays nicely with analyzing optimization. So I'm like extremely excited by this, but okay, little by little. I'll say some things about it, but that's kind of the fundamental problem. Okay, so are there comments or questions about this? There's still a couple minutes. I want to say a couple more things, so that's very good. Is that kind of clear what I'm saying? Only kind of. Yeah, please.
That's out of curiosity. You spoke about natural language application.
Yes.
Are there specific field where it is known to work very well?
Yeah, natural language processing.
Others.
Oh, I mean, this works extremely well in computer vision problems. I don't know. So I know this kind of thing is used. I don't want to lie. I know people try to use this kind of thing in mathematical finance, for example. But for other fields, for generic reinforcement learning, I don't know how widely this approach is used. I actually think it's used to some extent, but I'm not sure. But I mean, like it's used a lot for medical imaging. Okay, that's like a computer vision problem. But you train this to classify animals, and then you use it to classify tumors and MRI data, and it works phenomenally well. Why? It's not 100% clear. The best I have. Let me erase this. So let me now zoom out for the last couple minutes, essentially, and tell you something sensible about what I hope to accomplish. So there's a fourth question I was going to talk about, but I don't think I should do it. If there's time, I'll do it at the very end. Okay, so let me tell you what to expect for lectures 2 and 3. And then this will give you a sense about whether or not you actually want to listen to lectures 2 and 3. Okay. Maybe you just like my jokes, and that's okay. But maybe not. Okay, so here's how lectures 2 and 3 are going to go. They're going to be certainly more mathematical. So I'm going to say, okay, let's consider one of these fully connected networks. And okay, so I'm going to write out the definition of the fully connected networks, but this time I'll write it in components. So I'm saying, when I put an I here, right, this was a vector that lived in n(l+1) dimensional space. So I is what's called the neural index. It runs between 1 and l+1, right? And so what was the formula for this thing? So this looked like this. There were two cases, essentially. So the generic case is that it was a bias plus a linear combination of the previous things you got in the previous layer, WLij, sigma of ZLj of x. Right, so this is when L is greater or equal to 1. And when L is equal to 0, it's slightly different precisely for the reason that you pointed out. You don't apply the nonlinearity, right? So you get the sum, A goes from 1 up to NL of W at 1 and 0, W1ij, and you just get X sub j, right? And this is when L equals to. So this is like just a way in components to rewrite the definition that I started with for a neural network. Okay, and so what am I going to hope to do with these things? The first thing I'm going to do, and this is what I'll focus on a lot, though not exclusively, I'm going to start by talking about initialization, how you start optimization. Remember, step 3 in the training procedure was you choose random weights and biases. That's how you start your optimization. So I'm going to tell you how you do it. So with random weights, biases, namely, what I'm going to do is the following. So I'm going to take the weights WL+1ij to be Gaussian, mean 0, the variance a certain constant, which I'll say quite a bit about, divided by the width of the previous hidden layer. Okay, it may not be completely obvious, but this is the right scaling with the width. You want at least these matrices of weights to have reasonable singular values. Okay, this is the correct random matrix theory scaling for the W's, and the B's will just be some kind of Gaussians, mean 0, variance CB. Okay, so CB and CW are constants, and they're actually quite important in practice. So this kind of goes to your question. You actually want to initialize a network, you have to tell me which variances to use. Okay, you don't have to tell me, you have to tell the computer what variances. So CB and CW are what stand in for that. Okay, and here's going to be our goal. This will be like the first part of lecture 2 and the first part of lecture 3, and then we'll talk about optimization as well. Okay, so goal is to understand the distribution, so the law of this random field you get, CL+1 of dot. Okay, so if you choose the weights and biases at random, then you have some random mapping that goes from Rn0 to Rnl+1. The functions you start off with, it's this kind of green density that I was vaguely drawing before. So I want to understand this law in the following situation. When my hidden layer widths, so the width of the first layer, the width of the second layer, and so on, the width of the out layer, grow proportionally to some large number n. So I'm going to study networks that are big. I told you the width is pretty big, so I'm going to study wide networks. Okay, so what's the point of doing this? Let me erase this. That. Why do I care to study the random neural networks? Well, I've already given you some motivation for it, but there's actually more motivation than I've given. So let me briefly discuss that. And then I'll draw a picture and then I'll be done. Okay, so motivation. So why do I care to understand the distribution? Start of training seems like a horribly mathematical thing to do. Okay, it is a horribly mathematical thing to do, I have to admit. But nonetheless, it's also a horribly machine learning thing to do. Okay, so motivation number one is to do this. So if we can do this successfully, we're going to describe, like the answer to this question is going to describe the network at initialization at the start of training. And it's going to give principled ways to select all the hyperparameters you have to choose. So you might ask, how do you choose the initialization? How is the correct way to choose the hidden layer widths? What's the right way to choose the depth of the network? What's the right nonlinearity to use? How do you choose the step sizes for optimization? And so on. You see, there are many things which I didn't quite emphasize, but you really have to choose all of these things if you're actually going to use a neural network in practice. Okay, people spend a lot of time searching over good ways of making these choices and many other choices that come from more complicated architectures. But mathematically speaking, what you'd like is you'd like to know which combinations of these things give rise to neural networks that satisfy certain reasonable properties at the start of training. For instance, they're trainable. Okay, like imagine you start with a neural network where all the gradients of the neural network are 0 to machine precision at the start of training. That doesn't sound very good. You're never going to get anywhere, no matter how great your architecture is. And the point is, it's not completely obvious how to make these choices. Like the network is complicated and you have to have some theory to do it. Okay, so that's motivation number one. Okay, so motivation number two, and this is really going to be the subject, the second part of lecture 2, is the following beautiful thing. So it seems like the thing I'm planning to study is only about the start of training. And that's a little disappointing. But no. Okay, this is like the magic trick. Okay, so often, and I'll give a sketch of a proof of this. When the width of the network, when n is much bigger than the depth, that turns out to be the right way to measure the depth of the network. You can replace your fully nonlinear network, okay, the output z capital L plus 1 of x, which was very complicated, by its linearization. Okay, so let me write that. Call this star because it's exciting. And ZL plus 1 of x and theta. This is the thing that you thought you needed to actually do the optimization on, right? You had to optimize this theta. But it turns out you can simply replace it, at least in certain regimes, by just its linearization around the start of training. Okay, so this is the 0th order term, just the value, plus the gradient with respect to theta, CL plus 1 of x and theta naught, times theta minus theta naught. Okay, so the only parameters you're left to train in the linearization are theta. So that's an amazing theorem. Okay, it says that neural networks look really complicated, but at least if you fix the depth of the network, you let the width go to infinity. Okay, you do things in a more or less sensible way. In that regime, neural networks are simply linear models. Okay, it's a little disappointing. They're just linear models in this regime, but at least it gives you a place to start doing analysis, because linear models are things you know almost everything about. Okay, so you see, this is like the most important things. Okay, this is just a constant. It's not that important. But this is kind of the start of the game. The Jacobian, the derivative of the output of the network with respect to the parameters at the start of training. So if you can just understand the network at initialization, you get the full explanation of what the distribution of this thing is. And this is basically related to what people call the neural tangent. So I'll say much more about that before. But you might have seen the words NTK. And it's essentially just Jacobian transpose for this Jacobian. Okay, I'll say more. But the point is that by studying networks at initialization, in certain regimes, initialization essentially determines everything for training. So if you can tell me things about initialization, you can tell me things about the end of training too.
Is there a regime where you can get the center limit theorem from the parameters of this?
The short answer is yes. But the long answer is there are a couple of regimes in which you can get a central limit theorem from parameters. And the even longer answer is that it's like, okay, the longer answer is too long. Okay, so these are kind of my two motivations. That, like, I could put a 0th motivation that, like, for me, this is just a nice problem in like probability. I like it. It's a nice class of models, but yeah, that's like very subjective. Okay, so good. I have just a couple minutes left. So here's what I want to do. I want to give away, in some sense, the punchline of the next lectures to give you a sense of where we're going. Okay, I'm going to state some results. I'll draw a picture, and then that's it. Very, very good. Okay, so here's going to be the takeaways. Okay, so takeaway number 1 is like this. So the simplest thing to do, it turns out, is to fix the number of layers you have in your network, the number of times you apply sigma, and let the widths get bigger and bigger and bigger. Okay, so what are we going to learn? We're going to learn that when L is fixed, and L is the depth of the network. Okay, I just erased the network, unfortunately, because that was sad. That's bad move. It's okay. And you take all the hidden layer widths to infinity, and L go to infinity. Here you get some fixed input dimension, fixed output dimension. So you have some family of random functions from Rn0 to Rn1 that keeps changing as you keep changing n. Okay, so this family of functions is going to converge to a Gaussian process. Gaussian process at the start of training. Let's say at a minute. And that's what we call it in the biz. Initialization. Okay, so when you choose the W's and B's at random, the starting distribution, I kind of tricked you. I said it looks really complicated, but actually in this limit, it's very simple. It's just a Gaussian distribution. That's a beautiful thing. We know a lot about Gaussian. Very nice. So I'll actually give basically the full proof of that theorem. Say it's very easy once you know what to do. Okay, so what kind of Gaussian processes? So the Gaussian processes have mean 0, and they have a certain covariance. Kernel, which I'm going to write K capital L plus 1. Okay, so this is the covariance kernel for the Gaussian process after L hidden layers. That's my notation. And of course, these Ks, so I'll write it this way, it depends on what? It depends, I already indicated the dependence on the depth, but it obviously depends on the nonlinearity, and it depends on the variance of the weights and the variance of the biases. I mean, you need that to determine your function. Okay, so what we're going to find next is that the way to choose the variance of the weights and the biases relative to your nonlinearity sigma is to ask that as you vary L, these covariance kernels don't do anything crazy. They don't blow up exponentially or decay exponentially at L. Okay, so there's going to be, we borrow sort of a term from statistical physics, so what sometimes we call tuning to criticality. It's just the words may mean nothing to people, but I think of it that way. This just means, i.e., how to choose CB/CW such that K L plus 1 is a nice function of capital L. Okay, so there's like a lot of work between theory and practice, which basically says there's certain things you have to have happen at the start of training, otherwise you can't train your network. And the infinite width limit already gives you enough information basically to determine how to initialize your network. It's a really beautiful story. Okay, so the third thing we'll do is that I have smart, and I gave this a name, this exciting linearization, the fact that at infinite width, you can train your networks and think of them just as being linear models. So we're going to see that star happens. So with small step sizes, that's important. And L fixed n to infinity. Okay, so I'll give you the sense of the derivation for why exactly this occurs. Okay, that's called the linear regime or the NTK regime. Okay, and then the final thing, which I will actually do in the last lecture, but which in some sense for me is like a little unexpected at first, but then turns out to be like the heart of the matter, is the following observation. So you see, what I'm telling you is that if you fix the depth and you let the width go to infinity, neural networks are almost trivial. They just, at the start of training, are Gaussian processes. And for the purposes of training are linear models. It doesn't get any simpler than that. But these kind of networks have a big downside, which is they can't actually do transfer learning. They can't do feature learning. They don't do any of the interesting things I was saying real neural networks do. And the reason they can't do that is that only finite sized neural networks are able to do that. So instead of only studying the strict infinite width limit, we're going to study finite size corrections. Okay, so here's what we're going to learn. This is, I promise, the final takeaway. Okay, a little time, that's good. So at finite width, so you think of n as large but finite, and you ask, what is the distribution of the field, you know, like the random neural network you have? Is VL plus 1 of x. This field is determined by the following thing. It turns out that it's determined by, okay, if you want to be very precise, it's the sum of the reciprocals of the hidden layer widths. But really, just think of this as the ratio of the depths to the width. Okay, so there's a notion of like effective depth that appears. Effective depth. And it turns out that the right way to measure the complexity or how far a neural network is from being linear or how far a neural network is from being Gaussian or anything you want is captured not by the depth of the network as we usually describe it, not just by L alone. It's actually the ratio of L and N. Okay, and so what happens is you have the following kind of picture. So this is what I'll end on. You have this nice phase diagram, which I love to draw. And it goes like this. So you think of L being down here. So to the right, you get deeper networks. And you think of N being up here. As you go up, you get wider networks. And what you find is the following thing. Over here, if you fix the depth of your network and you let the width of the network go to infinity, you're in this really trivial regime. You get a Gaussian process, or for the purposes of optimization, you just get a linear model, you get the neural tangent kernel. That's this regime here. And the reason these networks are trivial is that the true measure of nonlinearity went to 0. Okay? A linear model is a depth 0 network, and the prior is a Gaussian process, and its linearization is itself. That's kind of the whole proof in some conceptual way. Okay, over here, if you make the network too deep, let's say at a fixed width, the networks become untrainable. They're too unstable to train. You can't do it. Here. Okay, but what happens is the right way to think about neural networks is by introducing a new parameter, which is the ratio of L over N. So this, so L over N is a constant. That's what these lines represent. So over here, the effective depth L over N equals 0. Here, the effective depth L over N is infinity. You're infinitely deep. And what happens as you actually increase L over N as you go this way, so what do you get? You get more feature learning. In other words, you are farther and farther from being a linear model. So that's good. It's like a regime in which you can actually study things. Okay, so you cannot understand the effective depth by passing only to infinite width. That's the point. The two limits don't commute. Okay, that's like the basic mathematical excitement of almost everything. The limits don't commute, so you have to do something sensible. So if you take the limit where L and N are both large, or more precisely, you have a finite size neural network, you want to know what happens, you actually do learn some features. You learn more and more features at larger depth. But on the other hand, it's also more unstable. It's harder and harder to train as L over N gets big. And this sort of suggests that you want L over N to be positive, but not too big. Okay, that's what people do in practice. It's some principled explanation. So I'm going to start explaining a little bit about this phase diagram if you want. Okay, so somehow like things that look like corrections that went to 0 with the width actually grow with the depth. And you can't neglect those corrections for understanding what real neural networks do. Okay, so I'm going to try to like explain much more about this picture, mainly in lecture 3. Lecture 2, I'm going to be talking only about the infinite width, this thing, and this thing. And if I have time, I'll talk about this thing as well. Okay, so we can look forward to that. But okay, I'm exactly at the end. So let me stop, and I'm happy to stick around and take questions.